Hey guys, so today I will try to demystify Windows kernel exploitation by abusing GDI objects. My name is Saif, I'm Egyptian, and I work for SensePost. That's the Egyptian traditional dress over there. Now, I want to start by saying why am I doing this. So, a year and a half ago, I started getting into binary auditing and wanted to do static analysis and finding vulnerabilities. And I found CTFs really enjoyable, but at the same time, they don't really represent real-world scenarios. So I decided to go for patch diffing and finding one-days. And the result was epic, and I hope you guys like it through the talk. So what we will learn through this talk is first, abusing two types of GDI objects to gain ring zero exploit primitives. The next thing is analyzing two one-days, MS16098 and MS17017 by using these techniques. Now, the complex is pretty complex. I will try to simplify it as much as possible. However, there is a full white paper and the slides and the exploit code and everything that is up on GitHub at the moment. You can access it on that link. The first thing that I have to talk about before we get into the juicy stuff is the kernel pool. You can think of the kernel pool as the heap memory that the Windows kernel uses. The first thing about the kernel pool is that any object allocated to the kernel pool will have a pool header attached to it. For 64-bit systems, this header is 8 bytes in size, and for 86-bit systems, this header is 8 bytes in size. The next thing is that small allocations or allocations smaller than 1,000 bytes will be allocated to a pool page that has the size of 1,000 bytes. So the kernel pool is effectively defragmented into 1,000-byte pages. And the allocation dynamics work as following. So the first allocation will be allocated from the beginning of the page. Subsequent allocations will be allocated by the end of the page. The next thing I want to talk about is kernel pool spraying. Why do we do kernel pool spraying or feng shui in the exploit development? First of all, it is used to get the kernel pool memory in deterministic state. The way it does it is by doing a series of allocations and deallocations. The series of deallocations is used to create memory holes that hopefully our vulnerable object will be allocated to, as thus having our vulnerable object allocated in a space between objects under our control that we can abuse to gain an extra exploit primitive or an extra access to the memory next to it. The next thing I want to follow through is kernel pool corruption. And we will focus about x86 integer overflows, or integer overflows in general. So the first equation I want to talk about is the FFFFF80 plus 81 will result in 1. Well, that's not really the truth behind it. The truth is that it actually results in a much larger number, 01000001. But x86 registers can only hold up to 4 bytes in memory. So this number is larger than 4 bytes max int, and the most significant byte or D word or anything that is larger than 4 byte length will be truncated, thus equals to 1. The first part I want to address is linear overflows. And this can be a result of mem copies with a larger size than the allocated object, or a memory copying loop that is larger than the allocated object. So if an overflowed size was supplied to an allocation object, it will result in a very small object being allocated, and then a memory copying loop or a memory copying function will try to copy a large number of data to that small sized allocation, effectively overflowing the next object in memory with the amount of bytes that it tries to copy. The next one is out of bounds writes. So if you think of an overflowed size that will allocate a smaller object, and then the function expects that object to be of a certain size and tries to write to a certain offset of it, it will effectively write this object or this data in an out of bounds location from the allocated object size. Now both of these, we'll see how we can exploit them when we get to the exploitation part of the one days. And now I want to talk about how are we able to gain exploitation primitives out of these type of pool corruptions. And one of the things that I'm going to focus about is actually the abuse of GDI objects. Now, there are certain objects that are allocated to kernel memory that has some interesting characteristics that can give us some sort of memory reading and writing primitives. For example, If we want to get a relative memory read and write, which is basically reading and writing in the memory location adjacent or relative to the object location in memory, the object that can be abused has to have a size member that can be extended to be able to access out-of-bounds memory adjacent to its location. If we want to get arbitrary memory read and write, the object has to have some sort of data pointer memory that if you can corrupt or control its value, you'll be able to read and write from any location in memory of kernel space. And if we look at the process of how this is done, if we consider that we have two objects that are located adjacent to each other, and these objects both have a size member and a data pointer member, we can use the first object or any pool corruption primitive to actually corrupt the size of the first object, thus extending the amount of memory that it can read and basically going to the adjacent object's memory, and then use the first object as a manager to actually overwrite the address or the data pointer of the second object and use the second object as a worker to read and write from any point in memory. Now, this exploitation technique can be used in kernel and is heavily used in browsers as well. The first of these objects that can be abused is the bitmaps. Now, GDI bitmaps techniques have been there from 2015. So the first people who talked about it was Keen Team, and it was later heavily detailed by Nico Economo, I hope I said this right, and Diego Juarez. The bitmap is represented in memory by a surf object and has a pool tag of GH?5, which represents a number that differs from one system to another. So this can be 0 or 1 or 2, depending on the version of Windows, or GLA5 when it's allocated to the look-aside list, which is outside of the stock. And this is how the surf object structure looks in kernel memory. So you'll notice that they're highlighted a couple of members, which are interesting to us. So first of all is the sizzle bitmap, which represents the width and height of the bitmap. So if you can corrupt any of these members, you'll be able to effectively extend the size and gain relative memory read and write. The other member is the pvscan0, which is a pointer to the bitmap data. The way you can allocate bitmaps to memory is by calling create bitmap user mode function. This takes a width, a height, the planes, the bits per pixel, and the bits of the bitmap and allocates a bitmap in memory. The way you can free bitmaps is by calling delete object. The next point is the way you can read the bitmap memory is by using get bitmap bits. These are all user mode functions. You can call them from any application. And the way you can write to bitmap memory is by using set bitmap bits. So how do we exploit or abuse bitmaps? Basically, if we consider that we have two bitmaps that are located adjacent to each other as a result of our kernel pool spray, if you have a pool corruption that allows you to overwrite the width of the height of the sizzle bitmap, that effectively extends this bitmap to write into the adjacent bitmap memory. And then we can use that as a manager and overwrite the pvscan0 of the second bitmap, and then we're able to read and write from any point in memory. The next thing I want to discuss is an undisclosed technique that has not been discussed anywhere. I just had a conversation with Scapy about it, and he mentioned that they have seen some in the wild, but it has not been documented anyway, so this is effectively sort of an ODay technique. And the way we address it, or the object that we use, is actually color palettes. So color palettes are interesting objects. They are represented in kernel memory by using the palette or the xepal object name. And they have the pool tag of GH number 8 or GLA8. This is the x86 structure of the object, and this is the 64-bit structure of the object. Now, the members highlighted in red are the interesting members to us. So you'll find that the C entries member, which represents the entries count of the palette, can be overwritten or extended, which gives us relative memory read and write primitive. And the second member that we can abuse is the p-first color pointer. So this is a pointer to the array of colors of that color palette, which is highlighted in green and usually allocated by the end of the object. So, you can allocate GDI palettes by using the create palette function that takes a logical palette structure that contains the palette entries as well as the palette entry numbers and the PAL version, and the palette entries contain the RGB color value for each palette. You can free palette objects from kernel memory by using delete object. And you can read palette memory by using get palette entries function from user mode. And you have two functions to actually write to palette memory in the kernel, which are set palette entries and animate palette. And we will look at the differences between them in a bit. So how do you exploit palettes? If we have a pool spray that results in two adjacent palettes be allocated in memory, and we have a pool corruption primitives that allows us to actually increase or extend the size or the number of entries of the specific palette, that will give us relative read and write into the adjacent object, which is another palette. We can abuse that by overwriting the p-first color pointer and use the second palette to read and write from anywhere in kernel memory. So there are some technique restrictions in regards to using color palettes in exploitation. First of all, the minimum palette allocation size for x86 system is 98 bytes, and D8 bytes for x64 ones. So when you corrupt the C entries member, it has to be larger than these values. The next restriction is related to set palette entries function. When you try to write to palette memory using set palette entries, if you clobber any of the current member, any of these members, it will block the writing to memory, which effectively will result in either a blue screen of death or will result in erroring out without actually writing to kernel memory. So the first restriction in regards to set palette entries, when you call set palette entries from user mode, it will reach GRE set palette entries, and then it will call XE pal object UL set entries. Like you see in the highlighted parts, the palette is actually checking for the P trans current and the P trans old, which are the transformations that happen on the specific color palette. If any of these members are set, it will try to access this memory location and then will try to end the value in it by 0. So if these memory locations were set and not allocated, it will error out without writing anything to memory. The next restriction is that when you call set palette entries and after the previous function was called, it will actually try to access the HDC head member, which presents the owner device context of the palette. If this value was set, it will try to get the owner of the palette to set its value in the device context. Now, this will effectively result in a blue screen of death, which will kill the whole system and not error out and not write anything. The second restriction I want to talk about is about animate palette. So animate palette has to have the pointer pointed to by p-first color has to be of an odd value. The first byte of it has to be of an odd value. And we know the reason why, thank you MSDN. So specifically, the animate palette will only work on entries that has the PC reserved flag set. And that flag is effectively 1, so that's why you can see highlighted there that the function tries to test for 1 before writing. Now, this didn't really represent any problems in x86 systems, since you can easily control where the palette is and control the first byte of the pool memory to be an odd value. However, in 64-bit systems, it proved to be a bit of a problem to set the first part of the address, since it's always FF. Now, we need to move on to the next step of exploitation. What we need to do is we need to try to steal the system eProcess token. And what this is that each process that is running on your system is represented by an eProcess structure in kernel memory. This structure contains very interesting members. It contains a member such as an image name, which is the exe name, and it contains a token. The token is the most interesting part of it, since this token represents the security permission that this process has. Also, it has a member that is the active process links, which is a double linked list that is actually pointing to the next eProcess entry in kernel memory, and the unique process ID, which is the PID of the current process. The offsets to these members differs from one system to another, and specifically for this talk, we'll be covering Windows 8.1 64 bits and Windows 7 SP1 for x86 bits, and these are the offsets to these members. And the game plan we have to actually exploit this or get the system token of a system process is, first, we need to get the address of the eProcess or the system's eProcess structure in memory. And the way we can do this is, actually, there is an exported symbol called PSA system process. So if you load the NTOS kernel.exe into your program's memory and get its offset and subtract it from the base of the NTOS kernel memory, you'll get an offset that this specific entry is located in the kernel. And then you can easily leak the NTOS base kernel address from the drivers and then just add this offset to it, and you successfully got the system eProcess structure location from the kernel mode. Then we use the arbitrary read primitive that we got to actually read the token of the system process and move on to iterating over the active process links until the process current ID or the unique process ID represents the current process ID, and use the arbitrary write primitive to just replace our current process token with the system one, effectively gaining an elevated type privileges. The first exploit I want to talk about is actually MS-17/017. Well, I really dubbed it that. I don't know if that's true. Microsoft has actually released it back in March, and that's the patch that I reversed, but it can be MS-17/013 as well, but I'm not very sure about it. It affects all versions of Windows, but I found it very difficult to exploit it on 64-bit ones, so I was only able to exploit it on Windows SP1 x86, and the function that is vulnerable is unreleased brush, and the type of the vulnerability is an integer overflow that leads to an out-of-bound write. First of all, the first step that I took to analyze this kind of exploit is to actually diff the patch that was released. It was released back in March 2017. This is the function that is vulnerable, which is unreleased brush, and this is the patch. So it was very difficult to find out where the problem actually is. As you can see, there were many changes. All of the changes were related to some integer checking mechanisms or integer checking functions. So I decided to look at the function itself. And the first step to do that is to actually find a way to trigger that function from user mode. So if you look, the first function we need to call is create pattern brush. And this will create a brush using a specific bitmap that you supply. And then you use a function patDLT, which actually writes the brush pattern to a specific path in memory. And then this will lead effectively to that function. So the way you do it in code, in C code, is this. This is actually an expert of the exploit code. So in the future, any of the code that is between this rectangle is actually expert from the exploit code itself. And the above code will reach this following IDA snippet with a controlled value in EDI. The first step that this code will do is actually get the value of EDI, which is the bitmap width, and then it will get ECX and multiply it with this value, which is at the time is 20, and this can be controlled by the bitmap format. And then it will divide this value by 8, and then it will multiply both values, the width and the height, after the following calculations, and then it will add 44 to it, which obviously, if you don't have checking leading to that function, you can easily overflow. But what happens on the overflowed function? So when I overflow the integer, what will happen later is the most important part. So if you follow the instructions of what happened with this overflowed integer, you'll notice that it will reach the following code snippet or the code branch, which is actually an allocation function. So this overflowed integer will be added to 40 again, and then passed as the size value for an allocation function. So if you remember, we said that if you're able to influence the size of any allocation and overflow the integer into a smaller size, then the allocation will result in a small allocation that is unexpected by the function itself or by the system. So after the allocation happens, we can try to trigger a specific number of bytes that the object will actually allocate. So we need a 10-byte object to be allocated, and we will know why 10 bytes specifically in the next slide. So we know that the overflowed value is 100000010, and then we have to subtract 40 and 44 from it, and we will reach the following number, which is FFFFF8C. And then if we take the result and look at the factors of that result, the factors of that integer, which represents which two numbers, when multiplied together, will actually result in that value, we'll come out to 8C and 1D4, 1D4, 1. If we take 8C as the width and effectively reverse the calculations that happened in the previous slide by multiplying it by 8 and then dividing it by 20, will result in 23. So if I take this and create the bitmap that will be used by the create pattern brush by having the width of 23 and a height of 1D4, 1D4, 1, I will effectively reach the allocation function with a controlled value of 10 bytes. And then after the function allocates the object, it assigns the address of the allocation to ESI. And the next step it takes is actually try to write to certain offsets of ESI. So the function is expecting ESI to be of a certain size, hopefully minimum of 84, since if you supplied 0, it will be added to 40 and then 44, and it will become an 84-byte structure. So what happens when we overflow it with a 10, when we actually allocate a 10-byte structure, is that the last highlighted in blue value will actually write to an out of bounds offset of the object. So ESI plus 3C is actually out of bounds. Since the allocation size is 10 bytes and it gets added to a pool header of 8 bytes, which makes it 18 bytes, so ESI plus 3C will actually write to the next object in memory. The problem is that this object actually is allocated at the end of the page. This object gets freed at the end of the function, which if you have it in the middle of a pool page, it will effectively corrupt the next chunk's header, and that will be a problem when it gets freed at the end of the execution, since it will the whole system will blue screen with a bad pool header value. So why specifically 10 bytes object? If you look at the calculation, the allocated object size is 10, and then the bitmap pool header, if it's an adjacent bitmap, is 8 bytes, and then the bitmap or the surf object starts with a base object of 10 bytes, and the offset to the bitmap height is 14, will result in 3C, which is the same value that the application tries to write to. So now we have 3 options. We can use this extended size bitmap to actually override the address of an adjacent bitmap, which is the old technique, and gain arbitrary read and write, and it will work fine. And then we can gain system. We can use the extended bitmap to demonstrate the arbitrary read and write capability of a palette object, or we can do a bit of work, and this is what we chose to go with, and use the extended bitmap to actually extend an adjacent palette to gain relative read and write and demo how the relative read and write in palettes work, and then use the extended palette to actually override the p-first color member of the next palette and gain arbitrary kernel read and write from there. The first things is first, so we need, as I mentioned, the object is allocated in the kernel, if the object was allocated in the middle of a pool page, then when the object gets freed at the end of the function, the system will blue screen of death. So how do we get over that is by allocating the object at the end of the page. So when the object gets freed, there is not a next chunk header, and the pool checking functions will not be able to check the next pool header, and thus the free will work normally, and the application or the system will not crash. And the first thing we need to do is, we know that the pool pages are separated into 1,000 bytes each, and we know that our object will be in total 18 bytes, 10 bytes for the object that we supply, and 8 bytes for the pool header. So we allocate a bitmap of size FE8, which will leave, we allocate around 2,000 of these till the pool memory becomes in a deterministic state, which will leave an 18-byte unallocated memory at the end of the pool. Then we use the window class memory menu name, which is available for this page session pool, to allocate 18-byte strings that will fill in the unallocated 18 bytes memory. Then we free the bitmap that we just allocated and continue to allocate an adjacent bitmap or a next bitmap of size 7F8, and then allocate palettes of sizes 7E8, effectively filling the 1,000-page or the 1,000-byte pool page with our controlled objects. Then we free some of the 18-byte menu names that we allocated, and hopefully, if everything worked, we should find our object allocated at the end of the pool page, as we see in front of you. So now the object is allocated in the end of the pool page. When the function frees the object, it will free it fine. And also we have an adjacent bitmap, and if you remember the calculations, that if it writes to 3C, when it has an adjacent bitmap, it will actually extend the size of this bitmap. So when we look at the adjacent bitmap in memory, we'll notice that in the first part, or in the top part, the size is 1A8 by 1, which is the width and height. And after the overflow or the out-of-bound writes happened, we noticed that the size would be 1A8 and the height would be 6, effectively extending its size, and it will effectively read past its bounds. So the next step to do is to actually extend that bitmap object to read and write to the next adjacent palette and change the C entries member from 1E3, which is the original size of the adjacent palette, to FF, effectively gaining relative read and write to 4 gigabytes of kernel memory. So how do we find this manager palette in the allocations? So we have around 2,000 palettes that are being allocated in memory. How do I find the specific one that was extended? Is by looping over the get palette entries function until one of the get palette entries calls will result in the return value of a larger number than expected, which is the size of 1E3. So until we find one that returns a number like larger than 388, that's our manager palette that will be used to actually overwrite the next palette in memory. So if we look at the next palette in memory, the top part is before we actually try to overwrite to, and we will use set palette entries on the manager palette to actually set the p-first color and update it to a value under our control. So some of the data that we were reading using get palette entries will contain actually some pool addresses. That will allow us to leak some pool addresses and calculate from it a header address from one of them, which is the beginning of the pool page. So if we change the palette entries of one of the pool pages to the beginning of a pool page, effectively pointing to the bitmap header, since we need to get this header to actually fix the bitmap object, because if we leave it as is, or at the time we finish the execution, the system will crash because there were pool headers that were corrupted. So the way we can find it is again by looping over our allocated palettes using get palette entries, finding the first byte, the palette entry with the first byte of 35, which represents the number 5. And if you remember, the bitmap object has a tag of GH5, which is part of the pool header. So the first byte of that object will be actually 5. So then we can use the extended palette, which we extended its size as a manager palette, and use it to set the p-first color of the adjacent palette object of the worker palette object, and then use the worker palette object to actually gain arbitrary kernel read and write. So the next step would be to use these primitives to actually read and change the current process token privileges. So we start by getting the initial system process, and as I explained earlier, calculating the address of this kernel system process, and then using the arbitrary read to read its security token, and then use a kernel write to replace our own, and we will see now directly exactly how this happened. So we start by using a low privilege user, and I've put in the code some debug breaks, so when we execute the code, it will actually break on kernel memory. We just reload our symbols again, and we find our place. So on the right is our code. We trigger the overflow and break on the allocation functions to see where exactly, if everything went right. And you can see the pool layout went correct. So we have our object allocated at the end, and we have an extended bitmap and our manager palette and the worker palette in there. I'm sorry if it's a bit fast. All the videos would be available on the GitHub page. And then I modified the GDI object WinDebug extension to actually dump the structure from a pointer. We can see the original bitmap size, which was 1 and 1A3. And after the overwrite, we can see that the height of the bitmap changed to 6. Next, we view the palette object that is adjacent to this bitmap to see if what changes happens in memory. And we notice that its original size is 1E3. And then after we use set palette entries to actually overwrite its members, we notice that the size will change from 1E3 to FF. And now if we take a look at the next palette entry in memory, we'll notice that the p-first color member value is the default value or the original value. And after we override the value using set palette entries, the value has changed, pointing to a beginning of a page or a bitmap object. And if we dump the memory that is located at this location, now this is the updated p-first color. And if you look at the memory that is in that location, we'll notice an original this is the clobbered bitmap header. And we already read the original bitmap header, and after we write to it, we successfully modified the header to a fixed one. And this is going over the eProcess token stealing. So if you look at the eProcess structure that is saved in our code, and dump the image file name and token, we see that this is actually a system process and that this token is the system token. If we move on to get our current process itself, we notice that the process name is exactly our exploit name and the token is a normal token or a low privileged user token. After we use the arbitrary read and arbitrary write to actually replace our current process token with the system one, this means that we successfully actually got system privileges, and when we continue execution and go back to our virtual machine, when we will notice that we are actually system now. So that's the first exploit I wanted to talk about. So from a low privileged user, I'm using GDI objects and I'm using GDI palettes to effectively gain system privileges on a system, basically doing an elevation of privilege from a low privilege user. The next exploit is MS16/098, which is a region object affecting the region object, and it's an integer overflows leading to a pool overflow. If you look at the start by patch diffing, we notice that the function ulong_multi is added to the fixed function, which effectively checks if the two integers supplied will result in an overflowed value, and then it will pass this value back to an allocation function. That's the patched version. The unpatched version, though, will do some calculations on a register and then pass the value directly into an allocation function that will allocate that value. So again, how we reach this function, if we look at the function syntax that is defined in IDA, which is bfill function, we'll notice that it works on ePath objects. So the way I did it was I just Googled for MSDN, fill, and path, and I reached the function fillPath. So when I call fillPath from user memory, and I take the example code out of IDA, I notice that I'm not actually hitting the function that I'm supposed to hit, but instead I'm hitting the first function of the series, which is engFastFill. By analyzing this function, I found out that it's actually checking the type of the device context that I'm doing this fill path in. And it turns out that it required a memory bitmap path device context. And this is the code that is used to actually reach the vulnerable function. So the next step would be to control the allocation size. So we know that the value is these assembly instruction load effective address RIX plus RIX times 2 into EACX is effectively multiplying this value by 3, and then shifting this value by 4, or a nibble is effectively multiplying this value again by 16. So if we get the max int value and divide it by 3 and then add 1 to it so we can actually overflow it, it will result in 55555556. And then to check if we multiply this value by 3 again, we'll notice that the value will be 10000002. Now that's before the shifting. So after we shift it by 4, it will result in 1000000020. And if you look at that value, and you know that this exploit is actually affecting Windows 8 64-bit, then you'll notice that this value will not overflow a 64-bit register. However, I noticed during my analysis of 2 exploits so far, that if some of the allocation functions, when they're getting called, the size is actually casted into a 32-bit register before the allocation, effectively truncating its value. So this value will be 20, which will be supplied to the allocation. Now, how can we actually control this allocation size? Well, I found a blog post by Nicholas Economo, which was great. It was for MS16/039, and the exploit code itself, or the vulnerable function, looks to be exactly copy-pasted from the current function I was analyzing. And he pointed out that the number of points in a given path is what actually controls this allocation value. So how can I control the number of points in a path? By using the user mode function polyline2 and supplying a point array. Calling this function 156 times with 3 FE01 points will result in a controlled value being allocated in kernel memory. So if you multiply the two numbers, it will result in 555556. Now, someone will tell me this is much smaller than the value that we discussed during the calculations, and you are right. And due to the shifting of 4, this value will actually result in 10000005, And after it gets shifted by a nibble, this value will be 50 and the 1 will be truncated. We do our pool feng shui and the exact same thing as the last exploit. So we allocate a large size bitmap. And you notice that this time I left an allocated space of 80. The reason being, at the time, I didn't know of a function that I can abuse, like the menu name, to actually allocate and deallocate small-sized objects. So I went with a weird way, with the next step allocating 2 accelerator objects which have a fixed size of 40 bytes, and then unallocate the bitmap, and allocate a region object of size BC0. Now this is just padding. We don't actually need this object, but if we allocate the bitmap adjacent to our vulnerable object directly, it will actually the overflow will not result in overwriting any of the interesting members that we find. And then we allocate the space that is left with 3C0 with our bitmap and free our accelerator tables. And hopefully, if everything went right, we should find the following pool layout, which shows that our object is allocated at the end of a pool page. So when the object is freed, it will not crash the system. And the bitmap and the region object is adjacent to it. So we needed to control the overflow, since if we overwrite this large number of points to a small allocation size, it will actually blue screen of death the system faster than we can do anything. The function responsible for copying points is bconstruct_get, and it calls add edge to get. This function will actually cast the previous point.y to R10 and the current point.y to R11. Then it will check the current point.y against a certain value, which on my system was 1F0, and it proved to be working on all systems. Now this value is actually a shifted value by 4. So the current point.y will be shifted by 4 and then compared to this value. If the value was more than if the comparison results in a value more than the 1F0, then it will not copy the point. If it's less, then it will copy the point. And this gives us a primitive to actually control how many points are copied to memory, thus controlling the overflow number. So the way we can control it is by actually setting in our point array the third point to 20 decimal, which is 14 hex. If shifted by 4 equals 140, which is less than 1F0. So until we hit a specific point of the polyline 2 loop, which is 1F iterations, that will copy exactly the number of points needed to overflow the bitmap height and width. So, before the overflow, on the top, we can see that the sizzle bitmap is actually 1 and 52. And after the overflow happens, the sizzle bitmap is 1 and FFFF, effectively extending its size. And where this value comes from is actually the same function that copies the point will subtract the previous point.y from the current point.y, and if it was signed, if it was unsigned, it will write 1 to that offset, and if it was signed, it will write FFFF to a second offset. We'll again loop over getmap this time to find our worker, and luckily enough, the next handle was the worker, or the next bitmap in memory. And we get some of the addresses that are leaked using get bitmap bits, and from them calculate the offsets or the addresses of the overflown objects so we can fix their headers. And then we can use set bitmap bits on the manager to actually set the pvscan 0 of the worker, and use the worker bitmap to write to anywhere in memory, arbitrary read and write. And then we use this to fix the bitmap and the region object overflowed headers, and ultimately steal the system token. And this is the video of it happening. So we're using a low privilege user, and we have debugger breakpoints set in our exploit code. We run our exploit. Then at this point I didn't know so much ASCII art, so it will stay black like this. Now we break at our debugger. We see that actually we are just before the vulnerable function, or triggering the integer overflow. So we break at the allocation, and after the allocation, after the write, and we continue execution. We'll notice that at the allocation, we control the value, and we'll be able to allocate a 50-byte object and try to copy around 5 gigs of points to it. which will result in direct overflow. But luckily, we found a way to actually control the overflow as explained earlier. And if we look at the layout of the pool after the allocation, we'll notice that it's the same layout that was shown previously. And we have our allocated object, the manager bitmap, and the worker bitmap. And we use the great GDI object dump extension after modification to actually dump these bitmaps from memory. So we can see the structures clearly. We see that the manager bitmap, sizzle bitmap was size is 1 and 52, and after the overflow or the point copying, we find that the size is now 1 and FF, effectively extending the bitmap reading or writing functionality to 4 gigs of kernel memory. And then we continue execution, and we can see that we can use this manager bitmap to actually overwrite an adjacent bitmap object, pvscan0. This is the original pvscan0 of the worker bitmap. And after we use set bitmap bits, we're able to overwrite it with a value that we control, pointing to one of the clobbered headers of the bitmap or region objects. And if we dump the memory, we'll see that this value of the header is actually clobbered and not a valid header. And then we use the leak addresses and the read get bitmap bits to actually read a proper header and fix the object's header. And then if we continue execution, we reach the part where we will stealing the system token. And now we verify that it's actually a system token and not any process. And this is the token value. Then we go into finding our current process eProcess structure in memory. And we use the arbitrary kernel memory read and write to actually override this value with a system process token. And we verify that our current process was actually overwritten by a system process token. And we just continue execution. And go back to our virtual machine to find that we are system. So the conclusions of this talk, that we have not only one, but a new undisclosed technique to GDI objects that we can abuse to gain arbitrary kernel memory read and write, and abuse kernel pool corruptions. We can identify, hopefully, and exploit the same type of vulnerabilities in kernel and in any other objects. And the tools used in this talk was IDA, BinDiff, WinDebug, and VMware. And guys, you can get a hold of me at my email or my Twitter handle. And if you have any questions, modifications, suggestions, or if you ever find Diego Juarez, because I really would like to meet him. There's not enough time to take questions on stage, so I'll be heading to the chill out lounge just next to this room. If you guys have any questions or have any suggestions, please catch me there. Thank you.